I will start with the gravitational waves, and Lisa talk about the stochastic background, and then discuss some of the challenges in how one searches for the stochastic background. I'll talk about this pipeline that's being developed, and then I'll conclude with some of my remarks on how I think we should go about this. All right, so gravitational waves, of course, are a prediction of theory of general relativity. Back in 1915, Einstein wrote down this equation here, and this is probably the simplest way you could write it, and I'll briefly discuss it. He then, about a year later, linearized it, looked at what this equation looks like in the limit when the field is very weak, and he found that this complex equation really boils down to a simple wave equation, where the thing that's waving is the metric itself, how we measure distances between objects. So in particular, if the physical manifestation of these waves is in stretching and shrinking the space. Specifically, if we have a wave that's, let's say, propagating perpendicular to the screen, and if we have a set of free test masses in this plane, then as the wave propagates through, it will shrink one orthogonal dimension and stretch the other, and then vice versa. This will appear as elongating the circle into ellipses along these two orthogonal dimensions. He also found that there are two polarizations, the plus and the cross, which are 45 degrees rotations of each other, similar to the electromagnetic polarizations. Now, going back to his equation here, on the left-hand side, we have the Einstein tensor, which hides inside two spatial derivatives. So the units on the left are 1/meter squared. On the right-hand side, this T here is the stress energy tensor. So it hides inside things like energy density or pressure and so on. So the units are newtons per meter squared. Of course, Einstein's big insight was to put an equal sign between the two, indicating that if you have energy or mass in some region of space, it will cause curvature. Now, to make the equation work, you need to insert a proportionality constant K inside, which has to have the units of inverse newtons to make the whole thing work. And in GR, there is only one way of getting inverse newtons, which is to take the Newton constant G and divide it by the 4th power of the speed of light. Those are the only two constants that you have to work with. G is a small number, C is a very big number, so this ratio here is very small. K is of the order of 10 minus 44, 45 inverse newtons, so very small in the standard units. And this has two very important implications. First, if you want to see some appreciable curvature, something that you can measure on the left-hand side, T has to be huge. So you have to have a lot of energy, a lot of mass moving at high speeds and so on, in order to at least partly counter the smallness of K. And that means that, if I wave my hand, I'm producing gravitational waves, but at the level of 10 minus 45 in standard units, so basically immeasurable. So we have to look for catastrophic events in the universe, such as the Big Bang itself and other processes in the early universe, or collisions of neutron stars and black holes, in order to get measurable gravitational waves. The other consequence of the smallness of K is that once the gravitational waves are created, if you want to disturb them, to change them, you again need some huge T, which means that the gravitational waves are very difficult to perturb, to change. And once they get going, they're essentially unperturbed until they're observed. So this gives us a unique opportunity to go after gravitational waves that are coming from the early universe, which is what phase transitions and topological defects would be like. So over the last 50 years, there's been a lot of progress in the field, of course. We all know about the discoveries by terrestrial detectors like LIGO and Virgo in the 10 hertz to 100 hertz frequency band. There's been also a lot of work on measuring the B-mode polarization of the CMB, which corresponds to very large scales or low frequencies, about 10 to minus 18 hertz. At about 10 to minus 9 hertz, people looking for gravitational waves by measuring the arrival times of millisecond pulsars, which is also yielding interesting results as of last year or so. My focus will be on this frequency range here around the milliHertz or tens of milliHertz, which is what satellite-based detectors are meant to cover, including LISA. So LISA stands for the Laser Interferometer Space Antenna. It is a joint European and Space Agency and NASA project, and it's expected to launch around 2035. It will have 3 satellites, as you can see in the schematic here. They're separated by about 2.5 million kilometers, and each of the satellites will have 2 lasers pointed at the other 2 vertices. So it will emit laser beams in both directions, and it will receive also lasers coming from the other 2 vertices. And by essentially beating these 2 laser beams, the outgoing and the incoming one, and counting the fringes, you can do the interferometry and essentially measure the distances between these 3 vertices. So the detector will be sitting at the Lagrange point, trailing the Earth around its orbit around the Sun. And it's designed to last at least 5 years. So it will certainly be operational for 5 years, and hopefully more than that, maybe even 10. This plot down here is meant to illustrate the richness of the science potential of LISA. There are many, many sources in the LISA band. This dashed curve here shows the sensitivity of LISA in strain versus frequency. And all of the other curves are corresponding to different types of sources, binaries usually, and so on, but we'll talk more about that in a minute. Oh, something happened. Oh, there we go. Now, the focus of my talk will be on the stochastic background of gravitational waves, which arises as a superposition of many sources that are not correlated. So really what we're talking about is noise. As such, it doesn't have any particular waveform that you can predict or search for. The way we would typically describe the stochastic background is in terms of the energy density that it carries. So the rho here is the energy density in gravitational waves, and it's normalized by the critical energy density in the universe to give us this dimensionless parameter omega. And the plot here is what we refer to as the landscape plot. It shows many orders of magnitude in omega and many orders of magnitude in frequency. And it has multiple detectors or observational areas. So for example, the 3G is the future terrestrial-based detectors. Here is LISA in the middle. The pulsar timing is down here, 10⁻⁹ hertz and so on. And all of these other curves are different models, both cosmological and astrophysical. Here is inflationary background. Phase transitions come in different varieties. Here is one that corresponds to electroweak symmetry breaking, but there are variations on that as well. Here are the cosmic strings, topological defects from the early universe that could give rise to a spectrum that looks like this. And then there are astrophysical things. So for example, galactic foreground of binary white dwarfs is down here. It's in the LISA band. The neutron stars and black holes of the solar size would also create a stochastic background that's sitting over here, spanning both the LISA and the terrestrial band and so on. So the point I think that I'm trying to get across here with this plot is that it's a very busy one. There is a lot going on, a lot of different models that are being proposed, and also a lot of different measurements. And this is where the difficulty really lies as well. So suppose that we have a model that we want to test with the gravitational wave observation. You would write down some sort of a likelihood that looks like this. You would take your data. This is the energy density that you observed. Maybe it's a function of frequency. Maybe it's also a function of direction on the sky or polarization and so on. And you would compare it with some model, which is also a function of frequency, and also maybe of some fundamental parameters, like the energy scale of the phase transition and so on. And then you would scan the values of the parameters and see which set of parameters gives you the best fit, right? Which one maximizes the likelihood. Now, if omega, or the observed omega, is null, if you have a null measurement, if you have not made a detection, then this game is very easy. You can just put in here models one at a time, excuse me, and find exclusion regions that look like this. So you plot maybe theta 1 versus theta 2, your two favorite parameters, and show which part of this parameter space has been excluded by the measurement. However, if you have a detection, the game becomes much more complicated because it's no longer clear what should go inside here. There could be multiple models, as we just discussed, some astrophysical, some cosmological, and they're all competing here. If you don't put enough, if your model is not complete, it will give you biased results. So this is something that one has to worry about, in order to do it, one needs an appropriate statistical framework to handle it. There are also other complications, not just the fact that there could be multiple cosmological models, for example, but also, as we saw earlier in this plot, there are many binaries at different mass scales, both of supermassive type and also of solar-sized black holes and so on. They're all at least partly in the LISA band, and they will all have to be taken out, subtracted before we look for the stochastic background. If you don't do it, then they're contributing to the energy density. So how do you do this? How well can you do it? Is there any residual once you subtract them? And how big is that residual? Is it going to bias your results or not? When you look for the stochastic background, these are all important questions to think about. And then on top of that, not everything is isotropic. We know that there will be a strong foreground from the galactic wide dwarf binaries. You have to model the anisotropy here as well. If you have an anisotropic background and you try to fit it with an isotropic type of a model, you will again get biased. And we've seen that with LIGO type searches as well. So you have to include directionality in the stochastic searches as well. So one way to approach this is to use the Bayesian statistics, this is of course increasingly being used in the gravitational wave field as well as in many others. And of course, the idea is to use the Bayes theorem, which I'm sure many of you are aware of. The idea, of course, is you have some sort of likelihood that tells you the probability of observing your data given some model and the model parameters theta. You multiply that with some prior on the model and on the parameters. So this is where your prior knowledge comes in. You normalize it by the evidence, which is the probability of observing the data itself. And out comes the posterior, which is the probability distribution for your parameters given the data. So this is very nice because it actually directly gives you the model parameter estimates, but it also gives you many other flexibilities. So for example, you can include multiple models in here in the likelihood. You can also add the detector noise as part of the model as well. And you can then handle multiple observations, for example, combining LISA with the third generation detectors or other non-gravitational wave observations and so on. You can use more complex hierarchies and so on. And you can also combine it with other searches, for example, for the binaries, and have one global Bayesian formalism to do it all. So I'll just briefly highlight one of these pipelines that we started to develop. It goes by the name of BLIP, and really Sharon here and Alexander have been doing the lion's share of this work. It's Python-based. It allows for a number of these things that I mentioned, like fitting the LISA instrumental noise, dealing with the stationarity or non-stationarity of LISA, because LISA will be actually tumbling as it goes around the orbit around the sun. It handles both isotropic and anisotropic sources. It allows the use of different samplers for Bayesian inference and so on. One of the really interesting things about it, and this is Sharon's idea, is there's a way to impose the physicalness here that the energy density is not negative. And the way he has done it is by defining a field on a two-sphere, this field S, which is a square root of the energy density on the sky. So if energy density is positive, then S is real, which means that you can impose this kind of relationship on the spherical harmonic decomposition of this field S. So the search actually works in the BLMs, which are the coefficients of the spherical harmonic expansion of this field S on the sphere, which is a square root of the energy density. And that allows us to impose that the omega, the energy density, is non-negative. We also decided to factorize the frequency dependence of the energy density from the spatial dependence, which is okay in many models, but not all. So that's another assumption that you just have to keep in mind. And then we write down our likelihood. I don't want to spend time on this, just to highlight that the way we have written it, the D here is the data. There are 3 channels of LISA, so this is a 3-dimensional vector, and C here is the covariance matrix. It's really the C that contains the information about the correlations and cross correlations of different channels. And that includes the noise of the detectors. It includes also the energy density due to different models. So the BLMs are hiding inside of the C, and that's how we estimate them. So here are some results. This is a recovery using blip of a point source using Lmax of 4. So this is when you expand in spherical harmonics up to L of 4, or Lmax of 6, and you see that with higher L, of course, you have better angular resolution, so the blob is smaller. You can try to push higher, but of course, as you increase L, the number of parameters increases. That increases your runtime and so on. So we decided to stop there, but there is nothing fundamental, as far as I know, to allow you to stop you from going further. So these are point sources, and you see the dots here are showing the true in simulated points, and you see that we are recovering them well, even though the blobs are relatively large. This is a recovery of an extended anisotropy. So Sharon has chosen some arbitrary power distribution that's shown on this plot. And then here is the recovery. Again, Lmax of 4. This is using 2 months of simulated data. This is using 1 year of simulated data. You see that with 1 year, you converge better. And in fact, the recovered map is very similar to the simulated one. This plot here shows the actual parameters. We refer to this as a corner plot. It shows each of these 2-dimensional plots is a 2-dimensional distribution for any pair of parameters that you may have. So the upper corner here, if you zoom in, has these 2 parameters, NA and NP, which refer to the noise of the noise contributions to the LISA detectors. And these 2 are parameterizing the frequency dependence, the amplitude and the spectral index of the frequency dependence. So you see that we're recovering them well. The vertical lines here are showing the true values of these parameters. So they're recovered well. And then if you go back to the full corner plot, the rest here are the BLMs, their amplitudes and phases and so on. And finally, as another demonstration, here's a recovery of the galactic foreground. In this particular case, and this was the work of Alexander Criswell, he assumed a relatively simple model, a kind of a toy model of the galactic foreground with some frequency dependence, and he managed to recover it well. As you can see, the left is a simulation, the right is recovery. And he's now in the process of actually doing a more sophisticated model using population synthesis to also try to recover some of the fundamental parameters of this distribution. So I think I have to finish up. Yeah. Basically, the main message I'm trying to get across here is that when we look at theoretical models, including the phase transitions and topological defects and so on, they will produce a stochastic background in gravitational waves, but there are also many other models that come into the mix, and there is a noise, and there is directionality and polarization and so on. And when we think about can we observe these, or how do we do parameter estimation for them and so on? How do we constrain these models? We have to think of it in a more global sense when we put everything into a larger mix. I think we need to have a unifying statistical formalism that will allow us to handle all of this. And there are already ongoing efforts to do this, but I think it's going to take a good part of the next decade to figure this out. So if you're interested in this, it's a good time to jump in. I'll stop here.